This is a talk about all of the research I did. Everything is on my website, and they'll be on yours. So we're going to start with a refresher about common mode and differential mode currents on lines. First, differential mode current is the ordinary power flowing through a transmission line to the antenna. It's between the two conductors. So the same current is flowing in on one and out on the other. And that's true whether it's coax or whether it's two-wire line. We'll start by looking at a simple dipole. This is a resonant half-wave dipole fed by two-wire line. I don't like to say balanced because the line is not balanced. Balance is defined a different way. But here's our simple dipole. And we have the two currents flowing. So the field exists between the two conductors. There's away from the two conductors, there's nothing. With coax, of course, it's inside. As long as we have only differential currents, there's no radiation because the field of one conductor perfectly cancels the field of the other. Common mode current is equal and flowing in the same direction on all conductors. In other words, it is it's an antenna current. It's flowing lengthwise on the line. There's no cancellation because it's imbalanced. It's due to imbalance. And so the line is will act as a long wire antenna. It radiates and it receives. There are lots of ways that antennas can be unbalanced. The earth can slope underneath them. The antenna can slope. We'll talk now about what makes a system unbalanced and or what makes it balanced. The impedances of each conductor to the reference plane must be equal. Balance is not defined by voltage or current. So imbalanced impedances cause unbalanced currents. Most ham antennas are unbalanced by their surroundings, even when fed by a balanced source and two-wire line. So we can have unequal capacitances to nearby conductors, unequal inductive coupling to nearby conductors, trees, buildings, towers, feed line coming off at an angle, and we don't even have coax involved yet. We're still talking about two-wire line. Now, coax will change the imbalance. It can either add or subtract from it, depending on where the unbalance is. But the unbalance is independent of coax. The fields around coax and two-wire line are very different. With coax, we know, and this has been known for many years, that skin effect splits the shield into two conductors. The inner skin carries the differential mode current, and the outer skin carries the common mode current, the current due to the imbalance. And all the differential power is confined inside the coax. All the common mode current is outside the coax. And a ferrite core surrounding coax sees only the common mode power and field. So when in two-wire line, when the two currents are equal, there's no radiation. When they are not equal, there is. And all of this, of course, works both for receive and transmit because of reciprocity. So now we're ready to talk about common mode chokes. It's a circuit element that reduces common mode current by adding a high impedance in series with the common mode circuit. It reduces radiation from the line and reduces reception from the line. Some history of common mode chokes was a coil of coax at the antenna. Terrible choke. A string of ferrite beads around coax that Walt Maxwell developed. His was a very good choke. And the only shortcoming of it, that the ones that were built and sold were really half-assed implementations of his design. The next form was multiple turns of transmission line through a toroid. Joe Reisert worked on that, W1HIS did, and I came along on it. Most one-to-one balance are common mode chokes, but not all good, not all are good common mode chokes. And here are some examples. So why do we want transmission line chokes? We want to isolate the antenna from its feed line. We do that because we want to reduce receive noise. That is the primary reason we use chokes. The secondary reason is that to keep RF out of the shack. And RF is often in the shack because we've screwed up bonding. We'll talk about that a little later. And we want to minimize antenna interaction for field day, SO2R operations, and some other situations I'll tell you about. The only good place for a common is up here at the feed point. And that's the only place it can really isolate it. We can add chokes at other places. But the only place where the common mode choke disconnects the antenna from the feed line is if the choke is right at the antenna. We got to understand that this is not a simple series circuit. When there's common mode current, that feed line is part of the antenna. It's not a DC circuit. It's an antenna circuit. So currents and voltages will vary along that feed line on the outside of the feed line or on the common mode, depending on how it would do on any other antenna. Another reason for using common mode chokes is as an egg insulator. This is an AM broadcast tower photograph at WBZ in Boston, 50 kilowatt clear in the middle of the band. And here you see egg insulators. Why are they there? Because we don't want any of these guy wires to interact with the antenna. We do the same thing in my station, for example. I have high dipoles up about 125 feet, lucky me with the redwood trees. Those feed lines can act as a parasitic element to a nearby antenna. So a choke acts as an egg insulator to break it up and prevent that interaction. I use them that way to prevent interaction with my 160 meter T vertical. And there's kind of a schematic of it. Now you say, well, it's close. Well, my 120-foot tower with antennas on top acts as a reflector for the T vertical, giving me a couple of dB or so of gain to the south, making me 3 dB weaker to the north. And though the tower and the T are 210 feet apart. On a 160, that's not very far. So in summary here, the first choke always goes here. We can use chokes here as an egg insulator. And if you need a choke down here to clean up RF in the shack, you got a bonding problem. And I'll show you a link where you can learn about that. N0AX has written a really good ARL book on grounding and bonding. And so by all means, buy that. It goes into a whole lot of detail. And this is a slide deck for a talk that I've done at Pacificon and Visalia and a couple of other places. Don't let that audio fool you. It is really mostly about RFI and lightning safety, but it also prevents hum and buzz. So let's talk about how common mode chokes work. These are the equivalent circuits of a ferrite choke. This is what it looks like at low frequencies. So it's resistance and inductance as a series circuit. The simplified circuit at high frequencies is that it's a very simple parallel resonant circuit, and this is the one we are going to think of most. But here is a more detailed circuit which shows how this resonance develops. You have R and L, and you have a parallel C. What's the parallel C? Well, it's mostly turn-to-turn capacitance, but there's also capacitance through the ferrite material, which is a semiconductor. It's an insulator. Here's a much more complete equivalent circuit that is very important for number 31 material, and it's why number 31 material is the only thing that's worth a damn on HF. Number 31 is quite unique in that it has a dimensional resonance based on the construction of the core, the cross-sectional dimensions of the core. So this is the resonance of the Y. Multiple resonances in the IF. Well, this is exactly how number 31 works and why it's wonderful. This is very interesting. Maybe 20 years ago at an IEEE EMC conference in Chicago, I met the two owners of Ferrite. Husband and wife team. She is the EE and he is the Kim E. And so it's a happy marriage of chemical manufacturing and engineering. I don't know of any other manufacturer that has done what Ferrite has done. So we're going to use this simple parallel resonant circuit to understand the choke, but the data sheets use this. And when we measure stuff with our VNA, this is what it's plotting. Now, the killer thing that the RS that the choke adds in series with the transmission line is what kills common mode current. So a very effective choke has a very high value of RS, RS being the series equivalent resistance. Going back to these equivalent circuits, these have fixed values. This is a fixed value of R, of L and R and C that are based on a particular choke. So for any given choke, these remain constant. But for this representation, they vary widely because they're all varying with frequency. And the way they vary with frequency is the same way that this parallel equivalent circuit would vary. Why is resistance so crucial? Well, we're trying to reduce the current. If we have a wire shorter than a quarter wave, it's capacitive. And if we have series inductance, it resonates with that capacitance and increases the current. A cable longer than a quarter wave and shorter than 3/4 is inductive, so series capacitance would resonate. But resistance always reduces the current if it's large enough. One of the important design characteristics here is that a high value of RS always reduces heating. That's because the power dissipated in the choke is I squared times RS. That is I squared times the resistance in the choke, where I is that common mode current. If RS is made larger, the current falls at the same rate as the resistance is rising. But since power is I squared R, power is falling twice as fast as RS is increasing. So basically, you can outrun your tail if you think about it that way. So if RS gets large enough, the current gets very small. The power in the heating due to common mode current gets too small to matter. So this is our fundamental design characteristic that we're looking for. Another excellent characteristic of this is that the high resistive value makes the choke much less sensitive to the feed line length. So now we're ready to talk about the cookbook. And the first question is, how did we get from these chokes, which I came up with back around 2009, to these chokes where we're building today? These are a couple of designs by my major mechanical collaborator, Glenn, W6GJB, who, by the way, is a great mechanical engineer, an aeronautical engineer, retired from the space program, had his own company. When I first met him, he told me, Jim, I'm one of those guys that knows how to catch the satellites when they come back. So here are a couple of his designs, and these are for inline chokes, the egg insulator kind of choke. Here's a design he came up with for a dipole center insulator. He built a bunch of these, did these on a CNC router. And after he'd done a couple, he said, Jim, I screwed up because this material is not good on your lungs. So he didn't do any more with this material, but very strong structurally. And we used up those insulators building his material. Here's another design. AB7E came up with this. W1LJ came up with this. And I'm sure there's a bunch of guys that have done some very nice mechanical designs. One of the characteristics is that you do want these chokes separated. You do want them in non-conductive enclosures, and you do want them exposed to air. And why did we change all of this? Well, this is what I had to measure with in 2007 to 2010 when I was coming up with these designs. Good stuff, nothing wrong with it. But all I could measure was the magnitude of the impedance. And it took half a day to get about 15 data points and plot them. So I measured only a few chokes of any given configuration. I hadn't learned that turns wound through the core out of order would cancel. Very important. Here's the test equipment that I have today and beginning in around 2016. This is a precision vector network analyzer made by some hams in the UK on the basis of a design by DG8 SAQ, an EE prof in Germany. And the test jig that Glenn designed for the chokes, for measuring chokes. This VNA is far superior to other ham VNAs. Nothing else is close. And the software is far superior, written by DG8 SAQ. You buy the analyzer hardware, and the software is free and very well supported. Why is it wonderful? Well, a lot more data points, much wider sweep range, which is very critical for doing TDR, time delay reflectometry, to see what's going on your feed line. And it does TDR by computing an inverse FFT from a single sweep. And you can use multiple windows to get the best view of the data. The software has a lot of built-in math. It can compute and display up to 6 parameters from a sweep, choosing from about 30 or 40 different parameters. It can be programmed to do lots of math, like what I did in Quattro Pro and a lot more automatically comes up on the screen every time I sweep. This is not a kit. It's fully built and tested. This is my recommendations if you want to buy one. And if you're serious about a VNA, this is the one you want. So the difference between 2010 and 2021 was I could measure a lot more chokes. I could get complex data. I could measure with far greater precision. And this let me see the shortcomings of the original designs. For those original designs, I was taking more than half a day to measure one choke. I was getting very limited data. It was point by point. I had to put the data in a spreadsheet, write the math to compute ZMAG, and plot it. And those are the plots that you see in my original RFI ham document. With this new test equipment, it takes about 4 to 5 minutes to measure a choke, record it, plot the data. I get the complex data. I get all of this stuff, all of this data plotted, and then I save a screen grab in 4 or 5 minutes. Component tolerance issues were obscured by the limited measurement precision and by the use of 4 to 6 cores in most chokes. So one of the things I did was study all of that. I got into the 2-wire line based on a suggestion or a request from GM3SEK, who observed that number 31 cores were either not available in the UK or were very, very expensive. So I built some 2-wire chokes wound with number 12 and number 14 THHN. They had very nice broad impedance curves, and they were much more repeatable because I was able to do it with consistent turn spacing. Here's one of those early chokes on a center insulator that Glenn built. This is before the new round of chokes. Glenn and I used a lot of them on their antennas. They were very effective, but there were a few failures. This is one, and this is another one. These are the only two I'm aware of, the only two that I've seen or that people have reported to me, although K6XX, who used some chokes, built some chokes, said he had some failures as well. Why did these fail? Well, for number one, it was a construction error. It was arcing to a nearby connector on the center form. But for number two, we don't know. We're only guessing. Maybe it arced when wet, maybe lightning, maybe a very high SWR when the operator screwed up. Holes when they failed. And as some of you know, I'm a serious contester, legal limit, CW, RIDI, sideband, and those were done with number 12 THHN. Another thing that we were able to get do with the new cookbook was that Ferrite had introduced a new, much larger core. And this looked very interesting to me. And I did a group purchase for a bunch of guys in the club, including myself. And we used these in our design, in our research, I guess is the right way to say it. And this is a larger test jig that Glenn built for measuring these larger chokes. So in order to study this component tolerance issue, which it's on the data sheets. The data sheets tell you that these are 20% parts. So I evaluated nearly a dozen winding styles using different cable, wire and cable types, different turn diameter and spacing, both of those cores. I eliminated the 1-inch ID clamps for transmit chokes because they're difficult to wind and maintain turns without out-of-order turns. These are the transmission lines that I studied. First, Teflon insulated number 12. enameled number 10 and number 12, THHN number 10 and number 12, white black from number 10 and number 12 Romex, which is awfully nice cable, and I ended up choosing it. And we studied RG 213 and RG 400. These initial experiments used special forms that Glenn built to maintain minimum bend radius of various coax types. None of these styles produced useful chokes. They were very expensive and impractical to build. Glenn built them on his CNC router. Not too many hams have got those. Luckily, none of them were useful. Here's one of them that he did. And we looked at these things for 1, 2, and 3 core stacks. Here's another one he did for RG 400. Imagine building something like that, huh? And to study the tolerances, I measured a standard winding on more than 200 numbered cores. I created a spreadsheet for the data and studied the variations in both RS and XS for that standard winding. That's what the standard winding looked like. So I had in my stash more than 150 of the 2.4-inch OD cores that had been purchased directly from Ferrite or from Ferrite distributors over a period of at least 10 years. They included the original pre-production sample I had from 2004 that Ferrite sent me when I said, you know, I really would love to have a toroid of that new number 31 material. And then about 70 of the large cores. These were all purchased as a single group purchase from a single Ferrite distributor. So we rejected all of those fancy forms. We rejected all coax other than RG 400. We rejected pairs larger than number 12 copper. Specifically the reason was that the larger copper didn't buy as much, and it limited what we could do with winding and made the winding more difficult. We also rejected the enameled copper pairs for a mechanism that was new to me, but not new to the world. A conductor by the magnetic field. It's the same mechanism as skin effect, but on steroids. So it increases the resistive loss in the transmission line, just like skin effect does. And it showed up in the transmission line measurements that I made testing the individual lines. We rejected THHN because it's got a nylon outer jacket that increases the OD a little bit. So with the NM, or the Romex conductors, we can get a few more turns on the cable. And the outer jacket of THHN degrades with UV, which is also a negative. So the chosen lines are Teflon insulated number 12, stranded silver coated copper, and the white black pair from number 12 Romex and RG 400. We also settled on a winding style of very close spacing so that we could maintain the best uniformly or consistency of turn-to-turn capacitance, which is mainly what establishes the resonance. Why did we use RG 400? Well, it was about power rating and the fact that we need to wind the turns very tight to the core, very closely spaced, which violates the manufacturer's recommended bend radius by quite a bit. RG 142 is a silver-coated copper coated solid steel center. But RG400 is a stranded copper center. The difference is both cables have Teflon insulation. They both have a silver-coated double braid shield, which makes the shielding very, very good. That's why these cables are very popular in repeater stations and similar installations. And the loss and shielding are equally good. Okay, so we're still winding very tight, tighter than the manufacturer's spec, but we're running well below rated power for that spec. We're at HF, and it's a one-time bend. That is the one time when we wind the choke. I consulted a bunch of colleagues, including Ward Silver, on this, and they considered it a very good compromise. And in support of that, RG400 is widely used by some commercial guys without failures. So our design with RG400 is a more conservative one. Buying it, Harbor Industries makes the best stuff I know of. They're based in Vermont and Quebec. They're part of the Berkshire Hathaway empire, and they make mil-spec cables. I found their cables on eBay, although recently they've gotten harder to find. An important note here is that the loss of RG400 and 142 are comparable to RG58. In other words, they're pretty lossy. So we don't use them any more than we need to use them. I'm using them only for chokes and for antenna patch cables for switching inside the shack. Why did we go with Teflon? Well, better performance. The measured data showed that. Better performance than NM, the Romex, and better performance than THHN. Has a much higher temperature rating, much higher voltage breakdown, and the characteristic impedance is close to 100 ohms, which is better matching to some antennas, like my high dipoles, which come in at about 88 ohms. You want to buy stuff? Spool ends and surplus can be found on eBay. That's where I bought everything I needed. These are 2017, 2018 prices. So about 160 per foot for a Teflon pair. NM is about 90 cents a foot for a pair, and you get a number 12 bare copper left over to do as you choose. Okay, let's look at transmission properties. One of the things that is left out of ARL publications in general, and all of the popular press and equations, is that VF, ZO, and the loss all vary with frequency. It is directly from the fundamental transmission line equation. It's true of all transmission lines. Here's some measured data for RG400. So we got a log frequency axis, and we have linear vertical axes. So dB per 100 feet is looking at this loss axis, and the impedance is looking at this axis. Notice that the characteristic impedance rises at low frequencies, and eventually becomes asymptotic to its nominal value up in the VHF range. Here's a plot of velocity factor and loss, but this time the loss is on a log scale. So I got log frequency and log loss. And this is a good way of verifying that your data is good. It should look like a straight line. Here's the velocity factor. So the velocity is slower at low frequencies. and once again approaches, becomes asymptotic to whatever the published number is at VHF. So these are the transmission lines that we chose. These are my measurements. The measurements on the paired line are not super precise. I don't have great confidence in them, but they're probably 1 or 2% measurements. Okay, to measure for the cookbook, what we're measuring is a parallel resonant circuit. So for each measurement, the choke must have 0 length leads, what my old EE profs used to say, to emphasize the importance. So for both core sizes, I selected cores with RS and XS values at their limits of the 150 cores in my stash. And I had figured that out in a spreadsheet. So then I wound turns of each line type to fill each one of these cores, and this took a while. I made a measurement with the core full. Took a measurement, did a screen grab, saved it, cut one turn, stripped the leads so that once again I'm looking at 0 length leads. Make another measurement. In another spreadsheet, I tabulated the RS values for each winding on each of the 4 limits cores. So in other words, what I've got is a spreadsheet with the worst case values of RS for all of the cores. And that's where the data for the cookbook comes from. So how much RS do I need for well-balanced and reasonably well-matched, I should say, and reasonably well-balanced antennas, 5 k ohms for noise rejection, and for transmit up to about 500 watts. If we want to run more power, better to have 10 to 15 k ohms. These chokes are designed for use at the feed point and in the feed lines of well-matched and reasonably well-balanced antennas. In unmatched, poorly matched, and poorly balanced antennas, they may fail, they may not work, and you may need 2 to 10 times larger RS values. These chokes are not designed for use in off-center fed or center fed antennas using open wire or window line as a feed line. If one or more chokes is used with these antennas, it should be wound with number 12 Teflon. It must be at the feed point, and it should have a very high RS value at all frequencies of interest. In other words, any place you're going to transmit through it. And even then, it could blow up. Okay, so now let's get to the cookbook. These are the tables that I did to make it easy to design your chokes. This is an example of one of the per band tables. So for 160 meters, you see the good choices for each of those 3 transmission line types. And there's similar data for the other bands. Here's another pair. Then here are some chokes that you can use in combination, in series, to cover multiple bands. So there are a bunch of recommendations for that. And here are comparable recommendations for the very large 4-inch OD cores. In essence, the only place those cores are really worth anything is on 80 and 160. They're a pretty bad choice anywhere else. I spent a hell of a lot of money learning that and a lot of time. Okay, then here are the tables and what the colors mean. There's kind of a key down here. So if they're not bold, they're useful on the band. If they're bold, they're better on the band. Bold red, they're great on the band. And if they're grayed out, not a good choice for the band. This is an eye chart, of course, so let's zoom in on it. So now you can kind of see what these numbers are and how they break. So this the right-hand side of the table is the attenuation in dB, and these loss numbers in watts now contribute or are used to compute these numbers for dissipation. So the differential loss is the loss inside the feed line as a function of its length and the inherent loss parameters. The actual dissipation will depend on the duty cycle. These numbers are for legal limit key down, but actual dissipation will depend on the duty cycle. So 25 to 30% for CW and sideband, 35 to 40% for WSJT modes, and 50% or more for RTTY contesting. And if you do rag chewing and key down, 100% duty cycle. The total dissipation is the sum of the differential mode, what is happening for loss inside the feed line, and the common mode heating due to the loss in RS, the loss in the core of the choke. And you have to compute that common mode number from NEC, that is an antenna design modeling software. So what you do is add a wire to the model having the diameter of the feed line with its physical length and layout approximating the geometry of what it's connected to. In other words, if this feed line comes straight down to the shack, then draw it that way. And if it's coax, it's going to ground at that point. If it's a two-wire line, it may be going to a balanced tuner, and you got to figure out what that balanced tuner is doing to terminate that line. So you add that wire, and then you add a resistance RS at the point where you've inserted the choke. R, and then correct that number for the duty cycle. So that's how you get the common mode loss in the choke. Then I had some cost numbers here. Once again, these are from 2018. We all know about inflation. So these the weights and the costs include the core, the coax or the wire, a couple of amphenol connectors, the good ones, silver Teflon with reducers, and some sort of simple structure to hold the choke. The length also includes 8 inches for leads and was used to compute loss. Okay, we talked about that. Okay, chokes need airflow. If they don't have airflow, they will fail. NA60, an excellent engineer, retired from the EMC world over in Illinois and retired to Silicon Valley, did some excellent lab work to quantify this as part of a project building matching networks for use at the N6RO superstation. And he confirmed my advice that without airflow, the enclosed chokes will fail. Here's a photograph of his, hang on, let me get rid of this. Okay, so here's a photograph of the enclosure he built for a matching network, and these are screened round holes screens to keep the stuff out, and so you got airflow in here, and something similar to that doesn't mean you have to do what he did. And notice you've got a non-conductive enclosure. Okay, we want to avoid conductive enclosures. For one thing, connectors that are bonded to the enclosure will short out the choke, which is duh. Proximity to the enclosure can detune the choke. All right, here are some guidelines for winding, which I developed, having wound probably 1,000 of them in the process of doing all these measurements. For paired winds, 2-wire lines, always use 2 different colors for a pair so that you can distinguish between them. Tie them together with Scotch 33, that's the thinner tape. And it may allow you to squeeze another turn on the 2.4-inch cores, which you might want for 160-meter chokes. I use very small cable ties to hold the winding in place. So you start with a cable tie around the core at the point where you want to start the winding and pull it not quite tight. So then you want to feed the winding through the coil from below and use a second cable tie to secure the winding to the first one. With both of these, leave enough of the cable to connect the choke when you're finished. And you want to snip both ends of the ties, but leave a cord. So there's a needle nose to pull the ties much tighter when you're done. Wind the turns in sequence very, very carefully. Out of sequence turns can cancel. Turns that reverse can cancel. Proceed around the core with each turn very tight to the previous one. Turns can be continued on a second layer when the core is filled, overlaying them over the start of the winding. And I did that for some chokes. Make certain that we didn't reverse. That's why where the different colors come in. Okay. It's important that we maintain polarity through a choke. If it's used in a coax feed line, you want the same conductor connected to the shield at both ends. This is quite critical for lightning protection, and it's also critical for chokes that are used in arrays. If the conductors are reversed, if the polarity is reversed, the choke will work, but the array won't, or it won't have the intended directivity. Let's talk about this word polarity because it's kind of new to hams. We had to learn about it in pro audio because having it wrong was a more severe train wreck than in the ham world. Polarity is the positive or negative sense of a signal, what we have wrongly called phase. Polarity is either normal or reversed. We change polarity by reversing the conductors or by passing through an inverted gain stage. Polarity is the same for all frequencies. Phase has meaning only at a single frequency, and it's a function of frequency and time. Phase shift in a transmission line increases both with frequency and its physical length. So a line that we think is a perfect inverter at one frequency is not if we go off resonance. That is, if we move up or down from the design frequency. This can be a very big deal in a broadband antenna. So it's important to understand the difference between phase and polarity. And I've been lecturing about this since I learned about it roughly, more than 50 years ago in the pro audio world. What about chokes with manufactured antennas? My advice is to always use the manufacturer's matching system, connecting it directly to the antenna. Then add one of my chokes between the feed line and that matching system. Why are we using one of these chokes? To improve noise immunity, prevent stuff picked up in the nulls from filling in the pattern, and to minimize coupling to other antennas in multi-transmitter operation. In arrays, the choke should be at the feed point of each element of an array. In other words, in a four square at the base of each one of the verticals. And we have to be careful that the length of line in the choke does not change the phasing of the array. So in a line like a four square where it's got to be a quarter wave, you've got to shorten the rest of the feed line to maintain electrical quarter wave. And that's a good place where you want to use good instrumentation to make sure you got it right. For use with 75 ohm phasing lines, or arrays with 75 ohm phasing lines, you can substitute RG302 for RG400 using the Cookbook guidelines. That'll work fine, and shortening the phasing lines as needed. The Cookbook includes guidelines for a miniature RG179 in four square arrays, where legal limit power is divided between the four elements. Okay, when you're going to rig chokes to directional antennas with a boom, capacitive coupling around the choke will detune it, making it ineffective. So you want to rig the chokes so that the coax on either side does not couple capacitively to the boom. For example, suspend the choke an inch or two below the boom, lashing the coax to the boom at a single point on each side of the choke for mechanical strength, but minimizing the length of coax in contact with the boom. A couple of thoughts about chokes. Compared to a single core choke, the same number of turns wound on two cores, that is a stack of two, will double the winding inductance, double the winding capacitance, divide the resonant frequency by two, double the impedance at resonance, and double the power handling. So that's for a stack of two cores. Identical single chokes in series have the same resonant frequency, and they double the impedance at every frequency. And they can handle 4 times the power because the current has been reduced by 2 and the power is divided by the 2 chokes. So each choke sees only half of that power. Here's a graphic example of that. This, by the way, is what I get from the VNWA. So here's the resonance, which is at 6 megahertz, and we got 5K. And now with 2 of them, the stack of 2, the resonance has moved down to 2.9 megahertz, and it's now almost same shape of the curve, basically. And here are the plots. This is XS. This is the reactance going through 0 at resonance, and the broad resonant peak, and the magnitude of the impedance, which is the sum of those 2. That's what I got. Here's some references. And the Cookbook is on the website, k9yc.com. And RFI-ham is the original ham tutorial about how chokes work, and a whole lot about RFI, and a whole lot about a lot of other stuff. And the last reference is a short cookbook that I did for VHF and UHF chokes. That's what I got, and I guess we're ready for questions. And I'm going to get rid of my screen share, I think.
Oh, fantastic, Jim. Thank you.
Yes, thank you, Jim. Great job.
Jim, I have used, I built those 6 and 7 core stacks from the early designs that we took with us to Honduras for one of our contest operations. But I'm glad with the lower airline luggage limits that now we can do it with 1 or 2 cores per band, and it's made life a lot easier that way.
Yeah. And that also ties in with what Ian, GM3SEK, told me about the costs. I mean, these are a lot cheaper.
Yeah. Oh, yeah. Definitely. And easier to make overall. Well, I know you've been doing yeoman's work on this. One of my good friends, W4EF, was Mike, was involved with you in the early days of the testing those things. And I know you guys went through an awful lot of work. So, and this is just kind of the culmination of a lot of dedication. So we owe you a lot for going through all that.
Well, Mike's work was absolutely fundamental at the early stage, and it really exposed stuff that he could measure better than I could at that point.
Yeah. That we didn't have the cool little VNAs like you described here. That's a nice tool.
Okay, I don't see hands up here. Jim, after we have the presentation here, can you send me, I see your hand there, Paul. Can you send me a copy of your slides, please?
Yes, I'll PDF it and upload it to you.
Okay, thank you.
At the link you gave me.
Okay, super.
That'll probably happen tonight or tomorrow.
Okay.
And it's on it will be on my website. What's on my website is a 4-year-old version, and I tweaked this a little bit, but not much.
There was somebody with a hand up, it went away. Did you change
That's
your
me. That was Paul.
Okay, Paul, go ahead.
I missed the first 24 minutes, so I'll watch the video when it comes out. If I'm using NVIS dipoles, up somewhere between maybe up to say 21 feet at most, and I'm using say 40, 60, 80, it sounded like the choke would only do some good at 80 meter or maybe 160 meter, and the others are no reason to build one. Would that be true?
No, it's useful having a choke on that line anyway. But I should talk about NVIS. Let me find that here, because I did a important piece of work on that a number of years ago. Let's see if I can find that. Why don't you talk among yourselves while I find it?
So yeah, if you put together something that would apply to those of us who are going to do an expedient antenna that's a dipole that's no more than 20 feet in the air that we can throw up for emergency comms, that's kind of where I'm at.
Okay, I tell you what. I'll tell you the result of my work. I did a very, very long study. It was a modeling study, but it was reviewed by some peer review guys. They're very, very smart. And they said, yeah, you got it right. What I studied was the effect of ground on horizontal and vertical antennas, and the effect of height on horizontal and vertical antennas. And I did modeling starting at about 20 feet and going up to 125 feet. And looked at the horizontal and vertical patterns. for horizontal antennas, the optimum height for NVIS is a quarter wave. And that holds no matter what frequency. If you go higher, you start losing upward. If you go lower, you get more loss in the ground. And that's a whole lot of very careful study. The other thing that you learn with horizontal antennas, let's put it this way. For 80 meters, my antennas at 125 feet are just about optimum. 40-meter antennas are optimum at about half that height, but going up to the greater height doesn't hurt much. And the criteria there is to work DX, is to work long haul stuff, which is low angle radiation. And the variations there in changing the mounting height is essentially changing the vertical pattern. That is, the higher you go, the more concentrated you are at low angles. The lower you go, the more you're sending up, or more correctly, you're losing a whole lot more in the ground. So it's one of the things that the shortcomings of ARRL's way of presenting antenna patterns and talking about takeoff angle is that it obscures the effect of height, or the effect that height has on ground loss. And the closer you get to the ground with a horizontal antenna, the more power you are using to warm the worms. And that power you're warming the worms with reduces your transmitted signal. So at any rate, that stuff's on my website, and it's k9yc.com/publish. Okay. So basically, you design your antennas the way you would. You want a resonant dipole, and stick it at a quarter wave, or as close as you can get to a quarter wave.
Jim, when you were referred to comparing, looking at ground, was this, did you notice a difference between high conductive and low conductive ground? Because we got horrible ground down here in the South, and some areas up north have much better.
Yes. One of the important conclusions I came to is that horizontal antennas basically don't care about the quality of ground. Vertical antennas are highly dependent on the quality of ground. That's why verticals work somewhere and somewhere they don't. So where we are, you and I, Marty, in very rocky soil in the mountains, verticals are terrible. The only place a vertical works for me is on 160. And the only reason it works on 160 better than a horizontal antenna is that at 125 feet, which is as high as I can get it, it's still a very low dipole. And when I moved in here in 2006, I put up a horizontal dipole up pretty high. I think it was 100 feet then. And I put up a T vertical for 160. And for 3 or 4 years, I ran AB between them. And there were very few times that the horizontal antenna worked better than the vertical. During the day, very interesting, the vertical would, with legal limit and a lot of radials. I started out with maybe 40, 50, added 30, added some more. I could get out 800, 900 miles during the day on 160. So where a 160 contest started at 2 o'clock, I can start working guys down around Phoenix, Seattle, Denver by 2:30, and that continues. That's with a vertical antenna. With a horizontal antenna, I don't even get a QRZ, and it goes on and on like that. So,
yeah. Well, as you say, it's at very suboptimal height from a wavelength perspective.
Yeah. Another part of the study I did for verticals was to answer the question, and this was kind of started with what Ward did 15 years ago for studying verticals. He studied, I don't know, a dozen verticals and a dozen tribanders, 2 different reports. His verticals were all on the ground with radials. But my study wanted to answer the question, what happens if I take that vertical and put it on the roof? In other words, what if I put it at, typical 20, 25 foot height of a roof? And the answer is, for almost all conditions of ground, it works better on the roof because we reduce ground losses and we slightly improve the vertical radiation angle.
Even with that large number of radials on the ground, huh?
What I'm talking about here is ground independent verticals or antennas with radials. Remember, if you take think about what radials do. If I have a vertical on the ground, I have to have a place for the return current to flow. I could drive a stake in the earth, but the earth is a big resistor. So what do I want to do? I want to put down radials so that the return current flows in them, which are a good conductor. You with me?
Yep.
Okay. If I start with 4, the current is divided by 4 and the loss is combined. And we have that I squared R thing going on, right? Well, if I double the number of radials, I reduce the loss in the radials. And each time I increase the number of radials, I'm dividing the current in each radial by that number. Okay.
So the loss goes down as the square of the number of radials, more or less.
Bingo. Or I think the number of radials, I have to think about that. But at any rate, that's the mechanism. And I don't know if I was the first to figure that out, but I may have been the first to articulate it, or somebody else beat me to it 50 years ago. But that's why we want, when we have a ground-mounted antenna, more is better. And there's a whole lot of studies that have been done. There's something on my website where I studied a whole lot of work people had done on 160-meter antennas. So that's something to look at. But I studied the work that a whole lot of guys had done. And the gist of it is that if you're on ground radials, their length is not as critical as more copper is better.
Very good.
Okay, looks like Starlink.
Example can, as long as you can.
Someone in the chat put a corrected URL for your cookbook. So
Okay, you go to k9yc.com.
that doesn't work. You have to put 2018 cookbook dash Pacificon.
Well, no, you're using search. The website is, first of all, the website is running on Linux somewhere, and so it's case sensitive. So you want k9yc.com/publish.htm. All lowercase.
And that'll be on the slides when you get them.
Yeah.
Okay. We'll make sure we get that out there for everybody.
So getting back to this whole radial thing, when you raise the antenna, the vertical, off of ground, you don't need as many radials because the radials are not coupled to ground. Okay, so 2 to 4 radials is enough if you've got a multiband quarter wave up there. Also, there are verticals that are essentially loaded half-wave dipoles. There's a whole series of those. The R12, I think, is one of those. And I've forgotten the number of the other one. The AV series. So those are essentially loaded half waves, center feds. And so they don't need radials.
That's similar to the old Tom Schiller designs that we used in some of our expeditions when we're operating near water, facing in good directions.
Yes, and Tom is a wonderful design engineer, and he has come up with some really neat things. And I studied several of his loaded verticals, loaded center fed antennas, and I built some myself, designs for field day and so forth. But his designs are wonderful. He's a very bright guy.
Yeah, we used them in Qatar. We used them in the Cook Islands. Used them in Honduras and the Gambia. They really worked well.
Yeah.
But again, you got to be near salt water, and that salt water has to be within about a quarter wave of the antenna.
Well, he's one of these really bright guys. Been there, done that in a very serious way, like AA7 JV, for example. George Wallner, my God, what a genius. What he's done with radio in a box and what he did to be able to work simultaneous CW and FT8 on 160, man, that's brilliant engineering.
Well, if there's no more questions, I don't see any more hands raised, and there's nothing more in chat going on. We'll probably should pull the plug and come back tomorrow.
All right.
With that, 73 is everybody.
Thanks again, Jim.
Good night.
Thank you, Jim.